Welcome to Instrunexus, where we simplify complex engineering into clear understanding. In this exclusive series, we'll explore the complete instrumentation design engineering lifecycle, from conceptual design and feed to detailed engineering, procurement, installation, and commissioning. You'll learn how each phase builds upon the other, integrating process control, safety, data integrity, and interdisciplinary coordination. By the end of this series, you'll see how instrumentation design engineering acts as the central nervous system of every industrial project, transforming design intent into safe, intelligent, and reliable operation. Control and instrumentation design is far more than just selecting sensors and controllers. It defines the operational intelligence of the entire industrial facility. A well-executed INC system ensures functionality, efficiency, safety, and the long-term operability of the plant. Every control decision influences process design, impacting not just performance, but also the capital cost, execution schedule, and the safety profile of the project. The true mandate of C&I engineering is to create the digital blueprint that guides construction, operation, and compliance. This includes defining key process parameters, control objectives, and safety functions early in the project lifecycle. Modern automation involves managing thousands of interconnected data points, where maintaining data accuracy and consistency is critical. To handle this complexity, engineers are moving from document-centric workflows to data-centric environments, using specialized tools that allow real-time collaboration across disciplines. This ensures that any change, even a single tag number revision, automatically updates across all related deliverables like P&IDs, datasheets, and I/O lists. That's the true power and criticality of C&I engineering. It's the nervous system of modern industrial facilities. The systematic identification and depiction of control systems rely on internationally recognized standards. These standards ensure clarity, consistency, and interoperability across engineering, procurement, and construction teams. The International Society of Automation, or ISA, plays a central role in establishing these frameworks worldwide. ANSI/ISA 5.1 defines how measurement and control instruments are represented graphically on piping and instrumentation diagrams. Its symbols and identification conventions serve as the universal language of process automation, allowing engineers, vendors, and constructors to communicate precisely and efficiently. ISA 20 standardizes instrument datasheets, ensuring every specification, from sensor accuracy to enclosure rating, is captured in a consistent, auditable format. ISA 84, aligned with IEC 61511, governs the safety instrumented systems lifecycle. It establishes how safety functions are identified, designed, verified, and validated, ensuring that process risks are reduced to tolerable levels. Standards like ISA 88 for batch control and ISA 95 for enterprise integration define how control logic, MES, and ERP systems communicate in complex facilities. Beyond ISA, global frameworks from IEC, ISO, ATEX, and NAMUR dictate how instruments are designed, certified, and tested, especially for hazardous environments. In C&I engineering, compliance with these standards is not optional. It's the foundation for design integrity, safety assurance, and regulatory approval. Following standards ensures that your design speaks the same language anywhere in the world. The development of control and instrumentation systems follows a structured, phased approach, ensuring scope maturity, cost control, and risk mitigation before major capital investment. The journey begins with the conceptual design, also known as FEL 1. Here, engineers define the overall control philosophy, identify key process parameters, and outline the system's required functionality. This phase provides the first estimate of control system requirements, initial I/O counts, and a high-level architecture. Next comes the front-end engineering design, or FEED, corresponding to FEL 2 and FEL 3. This stage establishes the project's technical foundation, confirms feasibility, and optimizes cost and schedule. FEED ensures that design risks are identified and mitigated before entering the high-cost execution phase. The final stage is detailed engineering, part of the EPC phase. Here, all specifications, drawings, and calculations are developed into construction-ready deliverables. It's the point where cross-discipline coordination between mechanical, electrical, piping, and civil teams reaches its peak. A critical lesson across all phases. safety must begin early. When functional safety requirements under ISA 84 and IEC 61511 are delayed until detailed design, costly redesigns often follow. Instead, by integrating inherently safer design principles from the conceptual and feed stages, engineers can eliminate hazards at their source, like designing systems that physically prevent overpressure or minimizing hazardous waste streams. Early safety integration saves time, cost, and effort, and defines the true value of disciplined C&I engineering. The design journey begins with a clear understanding of the facility's operational needs. During the conceptual design phase, engineers and stakeholders collaborate to define the system's scope, control objectives, and functionality. This is captured in the User Functional Requirements, or UFR document, the cornerstone that specifies what the control system must achieve. It includes details such as the level of automation, whether the system uses sequencing, interlocking, or full automation, the number and location of control rooms, and any special requirements like redundancy, high-speed communication, or future expansion. The next step is preliminary sizing and configuration. Engineers prepare an initial I/O schedule using early P&IDs, defining signal counts and control locations. This early estimation provides the budgetary foundation for the control system hardware, making accurate scope definition and cost monitoring essential to minimize project risk. Conceptual design isn't just planning, it's where clarity of purpose transforms into the architecture of control. The front-end engineering design, or FEED, refines the conceptual design into a comprehensive technical and economic plan. During this phase, engineers develop process flow diagrams and preliminary piping and instrumentation diagrams based on the heat and material balance from process engineering. The C&I team formulates the control philosophy and drafts the initial control narrative, defining how the plant will operate, the key variables, control modes, and operating procedures. At this point, the P&IDs typically progress to issued for approval, or IFA status, confirming alignment across all disciplines. Before entering detailed design, a feasibility design review, also called a gate review, is conducted. This ensures that all user functional requirements are met and that the proposed control system configuration remains technically and economically viable. Successful completion of this gate confirms that the project rests on a sound, validated foundation, ready for detailed engineering and execution. The detailed engineering design phase forms the execution core of the instrumentation design effort, transforming design intent into precise, implementable engineering instructions. The first key activity is sizing, selection, and specification. Engineers perform detailed calculations for instruments such as control valves, flow meters, and safety relief valves using data from the heat and material balance, line list, and process specifications. The result is the instrument datasheet, a comprehensive document defining measurement range, accuracy, materials, and electrical details, standardized using ISA 20 templates and serving as the contractual foundation for procurement. Next comes P&ID finalization and safety reviews. P&IDs progress to issued for HAZOP, or IFH, status for risk analysis using what-if and FMEA techniques. If risks are identified, LOPA and SEAL assessments determine additional protection layers. The C&I team updates control narratives and datasheets accordingly before issuing the final IFC drawings. Finally, engineers prepare installation and wiring deliverables, including instrument layouts, hookups, loop diagrams, and cable schedules, enabling the construction team to bring the design to life. Once the instrument datasheets are issued for purchase, known as Issued for Procurement, or IFP, the procurement phase begins. Engineers evaluate vendor proposals, comparing technical datasheets, test certificates, and simulation results to ensure every component meets the required performance, reliability, and service life standards. The focus then shifts to installation and integration. Instruments are mounted, control panels installed, and kilometers of cabling laid to connect field devices with the control system and communication networks. During this phase, data management and traceability become critical. Every physical change, configuration update, and cable termination is documented in real time, forming the foundation for as-built records, the definitive reference for future maintenance, troubleshooting, and system upgrades. This marks the transition from design on paper to control in action. where engineering meets operation. The testing, commissioning, and handover phase validates the functionality, performance, and safety of the installed control and instrumentation system. It begins with the Factory Acceptance Test, or FAT, conducted at the vendor's facility to verify the DCS or PLC configuration against the finalized control narratives and design specifications. A clear and detailed control narrative is crucial. It eliminates programming ambiguity and ensures an efficient, accurate validation of the configured logic. Once the system is installed, engineers conduct the Site Acceptance Test, or SAT, along with loop checks and functional tests, confirming that all field devices, interlocks, and control strategies operate correctly in the plant environment. Finally, the documentation phase ensures that every drawing and record, from P&IDs to loop diagrams and instrument indices, is updated to its as-built or reissued for construction status. This marks the official handover, delivering a system that is tested, documented, and ready for safe, reliable operation. The instrument index serves as the master database for every tagged instrument within a project. It is the single source of truth, linking functional design, procurement, construction, and maintenance records. Each entry in the index contains critical data: the tag number, product and model, its location within the plant, and the functional role it plays, whether for measurement, control, or safety. It also includes detailed specifications, such as measurement range, accuracy, and output signal type, along with document traceability to P&IDs, datasheets, calibration sheets, and loop diagrams. By maintaining these links, the instrument index ensures complete traceability and data integrity. Any mismatch between the P&ID and the index can lead to material takeoff errors, procurement delays, and cost overruns during construction. In short, the instrument index is the heartbeat of instrumentation design, ensuring that every tag, device, and drawing remains perfectly aligned across the project lifecycle. The Piping and Instrumentation Diagram, or P&ID, is the most critical engineering drawing in any industrial project. It serves as the centralized repository for process flow, equipment identification, and the overall control and instrumentation scheme. P&IDs illustrate how piping, vessels, control valves, and instruments are interconnected, using standardized symbols and codes defined by ANSI ISA 5.1 to 2024. These symbols ensure a common graphical language across disciplines, so process, control, and electrical engineers can design, verify, and collaborate seamlessly. Beyond showing what devices exist, P&IDs reveal how they interact. For example, how a pump's running status might automatically control a seal water solenoid valve or a cooling fan interlock. P&IDs also play a vital role during HAZOP studies, serving as the primary reference for identifying operational and safety risks. Their issuance status, whether issued for approval, HAZOP, or construction, marks key milestones in the project's design maturity. In essence, the P&ID is the control blueprint, the document that unites design intent, safety, and execution. The Input-Output List, or I/O list, forms the critical bridge between the physical instruments in the field and the digital control system, the DCS, or PLC. Its purpose is to map every instrument tag number to a specific hardware channel or logical address in the control system. A preliminary I/O schedule is typically created during conceptual design to estimate hardware costs, but the final I/O list developed during detailed engineering includes the exhaustive information needed for configuration. Each entry defines the tag number, service description, and I/O type, such as analog input, digital output, or communication link. It also specifies the signal type, for example 420 mA, Modbus, or discrete contact, along with the exact control cabinet, module, and channel address. In addition, safety-related signals are flagged for SIS classification. The I/O list ensures that every field device is correctly represented in the control system, making it the foundation of reliable automation. Instrument datasheets are the definitive technical and commercial documents that define the exact requirements of each instrument before procurement. Prepared by the instrumentation engineer, often using vendor catalogs and design calculations, the datasheet specifies every key parameter that determines how the instrument will perform in the process. It begins with detailed process conditions, including temperature, pressure, and fluid composition, all derived from the heat and material balance and line list. Next are the performance characteristics: accuracy, linearity, response time, and long-term stability. The datasheet also defines materials of construction, ensuring compatibility with process fluids, and includes electrical and safety requirements such as power ratings and hazardous area classifications. This document forms the technical contract between the engineer and the vendor, requiring strict compliance with specifications and applicable standards. Ultimately, the instrument datasheet ensures that every device delivered meets its intended performance, safety, and certification requirements, verified through rigorous engineering review and testing. The control narrative is a formal descriptive document that defines the operating principles, key variables, and logic of a control system. It bridges process design requirements with automation implementation, ensuring that the control system truly reflects how the process is meant to operate. A complete narrative explains how each system behaves under normal and abnormal conditions, detailing interlocks, sequencing, and automation levels defined in the user functional requirements. It also specifies alarm set points, shutdown values, and operating limits that guarantee safe, efficient performance. This document becomes the blueprint for automation engineers developing the DCS or PLC configuration code, and later serves as vital training material for operators. The quality of this narrative directly determines project efficiency. A clear, detailed narrative eliminates ambiguity, reduces programming errors, and ensures a smooth factory acceptance test. In essence, the control narrative transforms engineering intent into precise, reliable control logic. The control system architecture drawings and specifications define the physical and logical framework of the entire automation infrastructure. The system architecture drawing shows the topology of the control system, illustrating how controllers, networks, and operator interfaces are organized across the plant. It depicts the hierarchy of controllers, communication networks, and the connections between control rooms, local operator stations, and higher-level systems such as MES or ERP. The accompanying technical specifications detail the hardware configuration, including the selected DCS or PLC platform, processor capacity, I/O sizing, and cabinet general arrangements. Defining these parameters early, especially network redundancy and interfacing requirements, ensures that the system delivers the required performance, throughput, and scalability for future expansion. Together, the architecture drawing and specification form the blueprint that transforms an idea into a robust, connected control ecosystem. Instrument location layouts, often called general arrangements, define the exact physical position of every instrument, junction box, and control panel within the plant layout. These drawings are essential for construction planning and installation efficiency. They ensure that each device is positioned optimally, close to process piping and equipment nozzles, while maintaining the required clearances for operation and maintenance. The layouts also form the basis for routing cable trays and instrument air headers, helping designers minimize cable lengths and reduce overall construction costs. Proper coordination with mechanical and piping general arrangement drawings is critical to avoid physical clashes and ensure safe, easy access for technicians. In short, the instrument location layout transforms design intent into a spatially accurate, constructible blueprint, ensuring that every instrument is exactly where it needs to be in the field. Hookup drawings are standard schematic instructions that define how each instrument is mounted and connected to the process line or equipment. They act as the core instruction set for field installers, showing every detail needed for safe, consistent installation. Each drawing specifies the mounting method, such as a pipe stand, wall bracket, or process tapping point. It details the requirements for impulse lines or instrument air tubing, along with the type and quantity of fittings, manifolds, valves, and protective enclosures. Every hookup includes a bill of materials, listing all components required for installation and material takeoff. The C&I team uses these drawings to communicate directly with the piping discipline, ensuring that all small bore connections comply with the piping material specification and the required pressure rating. Accuracy here is critical, because even if the main process line is robust, a single error in the hookup can compromise the entire instrument interface. The loop wiring diagram is the definitive schematic that shows the complete electrical signal path for a single control loop. It begins at the field instrument sensor and traces the signal through junction boxes, marshalling panels, and safety barriers, all the way to the terminal block inside the control system cabinet. Loop diagrams are essential during commissioning, serving as the roadmap for loop checks, and later as the primary reference for troubleshooting instrumentation issues during plant operation and maintenance. Each diagram includes detailed information, wire and cable numbers, terminal identifications, and intrinsic safety barrier specifications. Together, these details ensure complete signal traceability from the field device to the DCS or PLC input card. In essence, the loop diagram connects the physical and digital worlds, defining the nervous system of automation that keeps every process under control. Cable schedules and block diagrams are critical documents used to manage the entire cable logistics of an industrial facility. The cable schedule is a comprehensive tabular list that defines every cable's routing, size, and termination points. Each entry includes the cable number, type, core size, from to termination locations, and required length. During construction, this schedule becomes the foundation for material takeoffs, covering cable, trays, and associated infrastructure. To achieve accurate lengths and prevent over-ordering, engineers use specialized intelligent CAD software integrated with 3D plant models, such as AutoCAD Plant 3D or Avava E&I. This integration ensures that cable routing avoids physical clashes with piping or structural elements while maintaining efficient, conflict-free layouts. In short, the cable schedule and block diagram form the digital roadmap for wiring an entire plant, ensuring accuracy, efficiency, and constructability across every discipline. Critical design review. Gates are formal checkpoints that ensure design quality, UFR compliance, and risk control throughout every phase of instrumentation engineering. Safety assessments are conducted in increasing levels of detail as the design progresses. The process begins with the HAZOP study, performed once P&IDs reach IFH status, to identify potential deviations and hazards in the process design. When unacceptable risks are found, LOPA and SIL assessments determine the level of functional safety required for each safety instrumented function. The C&I team then integrates these findings, updating instrument datasheets to ensure the selection of appropriately certified devices and refining the control narrative to embed safety interlocks and shutdown logic. Successful closure of these safety reviews leads to document release for issued for construction, IFC, confirming that the design is compliant, verified, and ready for safe implementation. Control and instrumentation engineering depends heavily on upstream data from process engineering. The C&I team uses the process flow diagrams, heat and material balance, and line list to perform instrument sizing calculations and to select suitable materials of construction. These inputs ensure that every sensor and control element is technically compatible with the process conditions. In return, the C&I discipline provides key deliverables to piping engineering, most importantly, the hookup drawings and their bills of materials. While P&IDs serve as the shared functional document linking process design and control logic, the hookup drawings provide the installation-level detail that connects each instrument physically to the process line. This two-way exchange ensures continuity in material specifications, pressure integrity, and design consistency across disciplines, transforming engineering collaboration into reliable, buildable design. Control and instrumentation deliverables serve as the bridge between system design and the execution disciplines, primarily electrical and civil engineering. For electrical engineering, C&I provides the key data that defines how power is distributed across the control system. This includes electrical load lists, detailing the power consumption of control panels, instruments, safety barriers, and heating elements. These inputs allow electrical engineers to properly size single-line diagrams, motor control centers, and distribution networks. C&I also issues cable schedules and block diagrams, which specify the type, quantity, and routing space needed for control and communication cabling. For civil and structural engineering, C&I provides weight and dimension data for panels and instruments, ensuring accurate load calculations and foundation design. Environmental parameters like seismic, wind, and soil conditions are also shared to ensure structural stability. In modern infrastructure projects, C&I even supports geotechnical instrumentation, supplying sensors and data acquisition systems used to monitor the health of dams, tunnels, and deep excavations. Together, these interfaces ensure that power, structure, and control integrate seamlessly, from design to execution. Effective project management in control and instrumentation engineering depends on rigorous document control and data traceability. During the execution phases, particularly phases 3 and 4, documentation must be maintained in real time using specialized engineering data management systems. These platforms ensure that every revision, approval, and change is accurately recorded, allowing engineers to confirm that the final as-built configuration truly reflects the original conceptual requirements and any safety modifications from HAZOP or SIL actions. Proper data management guarantees traceability, minimizes design discrepancies, and supports auditable compliance. All documents, from P&IDs to instrument datasheets and preliminary control configurations, must receive formal approval from both the project C&I engineer and the client before progressing through design review gates. In short, disciplined document control transforms design information into a trusted, traceable foundation for safe and successful project execution. The instrumentation design engineering process follows a structured, phase-gated flow that ensures progressive maturity of technical scope and safety verification. Its true purpose goes beyond designing instruments. It serves as the central information integrator, connecting process properties, operational logic, electrical infrastructure, and structural design requirements. Successful execution of IDE depends on 3 key pillars. First, standardization and safety integration. Adherence to ISA and IEC standards, especially ANSI ISA 5.1 for documentation and ISA 84 IEC 61 5 and 11 for functional safety, ensures that all risks identified in HAZOP and SIL studies are fully resolved before issued for construction release. Second, data integrity and traceability. With hundreds of interconnected deliverables, such as the instrument index, datasheets, and I/O lists, only integrated, data-centric engineering tools can guarantee consistency, efficiency, and reliable as-built records. Third, interdisciplinary coordination. C&I deliverables like load lists, hookup BOMs, and location layouts directly feed electrical, piping, and civil engineering, positioning C&I as the multidisciplinary hub of project execution. In essence, instrumentation design engineering is the art and science of unifying standards, safety, and information to deliver systems that perform safely, reliably, and intelligently.